frog in the throat, right out of the starting blocks. Hello, hi, in that nice, bold, big voice. Welcome to another ramble with me. Let's do maths. We are busy with the department's paper 1 from November 2023. Question 2.2. The following information is given about a quadratic number pattern. T1, so the first term is 3. T2 minus T1 is 9. Okay, the difference between the first two terms, the first difference is 9. And T3 minus T2 is 21. So the first difference is 21. So here's what we've got going on. We have T1 as our first term, T2, T3, T4, and this question is asking about T5, so I'm just going to go right ahead up to T5. We know that the difference between T2 and T1 is 9. So, right, to go from T1 to T2, we are adding 9. So T2 is in fact 12. And the difference between T3 and T2 is 21. So to go from T2 to T3, we are adding 21. And so that is 12 plus 21 is 33. Right, and we know that quadratic patterns have a constant second difference. So to go from the first difference to the first difference, we're adding what? 12. So that is going to be the difference between all of the first differences, right? Okay, so the next first difference is going to be 21 plus 12, which is 33. And then the next first difference is going to be 33 plus 12, which is 45, right? So to go from this term to the next term, we're adding 33, so that's going to be 66. And to go from this term to this term, we're going to add 45, which is, yeah, okay, it's disturbing me how off center this is. Okay, anyway, so that is going to be 111, right? Yes. Okay, so the difference between all of the first differences is 12. And then having worked out the first differences, we can work out the terms. Cool. So, oh yeah, they tell us that T5 is in fact 111, so yay. And I think it's perfectly fine to present your thinking like this. If it's your vibe, it's your vibe. I'm not really invested in trying to show it any more systematically. It's good enough for me. Good enough. Show that the general term of the quadratic pattern is that. Okay, so yeah, I thought I would remember my little quadratic pattern picture, but I never do, so I'm just going to work it out from scratch again. Oh, I do kind of remember it. I know that A plus B plus C is equal to the first term, and then the first difference is given by 3A plus B. Yeah, so that is the first difference, T2 minus T1. And then the constant second difference is the same as 2A. A, B, and C being the A, B, and C in the general quadratic pattern formula thing, right? So we can use this to figure out our A, B, and C. So in our case, A plus B plus C is equal to term 1, which is 3. 3A plus B is equal to the first difference, which we're given as 9. And 2A is equal to the second difference, which we found to be 12. Okay, so therefore A is equal to 12 over 2, which is equal to 6. Okay, and that's already looking good. 6. Right, and then next we can put it into this equation to figure out B. So therefore 3 times 6 plus B is equal to 9. So 18 plus B is equal to 9. So B must be negative 9. Looking good. Again, B negative 9. Then lastly, we can work out C by putting it into the last equation. Well, the last equation being the first equation. So that is 6 plus negative 9 plus C is equal to 3. So that is negative 3 plus C is equal to 3, and therefore C must be 6. And indeed, C is 6. Right, and so what that leads us to is, therefore, Tn is equal to 6n squared minus 9n plus plus 6. Okay, as required for us to show. Cool, nice. And then the last question says, show that the pattern is increasing for all n elemental natural numbers. Okay, so we want to show that Tn equal to 6n squared minus 9n plus 6 is increasing for all values of n that are natural numbers, which really are the only numbers we care about, because what on earth is term 1.5? Right, so to do that, we want to show that, so for example, let's just say hypothetically, right, if our Tn, and again we're only interested in this side of the x-axis, and even more specifically we're only interested with n is equal to 1, n is equal to 2, n is equal, but I'm not gonna fuss too much about that. I'm just gonna care about values of n that are greater than 0 as a start, right? So if our parabola turned out to be a parabola that looks like this, right, what that would mean is that there are certain values of n for which our quadratic pattern yields decreasing values, right? And then we get to a certain value of n where that changes, and then from there it yields increasing values. What we want to show is that nope, there's never this trend. Right from the starting blocks, right from n is equal to 1, our parabola is on the up and up. So it's rather something that looks like that, right? So the way that we can prove that, there's actually there's two ways I can think of that we can prove that, right? So the first, I'm going to start with what feels like the less obvious way for me personally. Oh, and I also do just want to flag that we don't really care about whether this is yielding negative values or positive values, right? All we care about is that this is the trend, and not all the way from here. Really, we only care from n is equal to 1, n is equal to 2, n is equal to 3. So even more specifically, We are not dealing with one smooth curve. We are dealing with a parabola looking series of dots. Okay, that's kind of giving straight line. Anyway, so that's what the sequence will actually look like if we were to graph it. Okay, so let's get to the two ways I'm thinking of proving this. Okay, I'm going to start with what feels like the obvious way. And the obvious way for me is the moment we mention increasing, what I want to show is that the gradient of this parabola for any value of n greater than 0, greater than 1, if we want to be even more specific, greater than or equal to 1, the gradient is always going to be a positive number, because that's what it means for a graph to be increasing, is its gradient is positive. So we can figure out the first derivative of this guy, which is 12n minus 9. And we want to see, okay, when is 12n minus 9 greater than 0? When is this first derivative positive? And we find that, okay, it is happening when 12n is greater than 9, which is when n is greater than 9 over 12, which is 3/4, right? And so therefore, for n being a natural number, right? So natural number, again, just remind ourselves, is 1, 2, 3, etc. Then n is definitely greater than 3/4, right? Because at the very least it's 1. So therefore, 6n squared minus 9n plus 6 is increasing for all natural numbers n, because the first derivative is positive for all of those values of n. So that's the one way that you could go about it. The other way that you could go about it is if Tn is increasing for all n in natural numbers, then what that means is Tn plus 1 is always going to be greater than Tn. And there is a difference between increasing and strictly increasing, but I don't think we care about that at this stage in our lives. And yeah, I actually don't know now. So yeah, technically, if just increasing, then these two are allowed to be equal, so you can have two neighboring terms that have the same value, and it would still be considered increasing, at least as I understand it. But I think for our sake, for the same reason that here I didn't include the case where 12n minus 9 is equal to 0, right? I think let's be consistent. So so I'm going to say, if Tn is increasing, then what that means is that every term, okay, is going to be smaller than its succeeding term, the next term after it, or every term is going to be greater than the term before it, right? So we want to show that this is in fact true for any n that we choose. So we can sub in n plus 1 in our formula for Tn, right? So Tn is that 6n squared minus 9n plus 6. Tn plus 1 will be 6n plus 1 squared minus 9n plus 1 minus 6. Okay, so this is what we are trying to establish. We want to see which values of n will make this inequality true, right? If it turns out that this inequality is only true when n is smaller than 3, then we know that, okay, our sequence is not an increasing sequence, right? Because in order for it to be increasing, we need this inequality to be true for any n, any natural number n. Okay, so we want to see where this will take us. So we have, oh, I scratched my eye and it's burning now. Burning, 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 burning. 9n minus 9 minus 6, and here we'll have our good old tn, 6n squared plus 12n plus 6 minus 9n, this is minus 15. Ooh, itchy eye, resisting. This is going to be plus 12n minus 9n, so that's plus 3n. Here we end up with 6 minus 15. Okay, right. So now we can move our terms around. Let's just get everything to one side actually. So I'm going to minus 6n squared plus 9n minus 6, and then do the same to this side. Okay, so now we end up with 3n plus 9n, which is 12n, and then minus 9 minus 6 is minus 15, and here we're just left with 0. Oh, I actually want my constants on the other side, so maybe I was a bit zealous in my moving things around. Okay, 12n is greater than 15, and then we want to say divide by 12, divide by 12, so n is greater than 15 over 12, which is 5 over 4. In other words, 1 1/4. Okay, so what is this telling us? This is telling us that tn plus 1, okay, tn is increasing if every term is greater than its predecessor. And an important thing to mention now, okay, no, it's not an important thing to mention now. Anyway, so we then said, okay, we want to see, oh, I messed something up. Oh. Okay, so back to how I was interpreting the result and actually what did get me a bit dizzy. So this result is saying this inequality will only be true when n is greater than 1 1/4, and low-key this would have pasamisad us because we want to show that actually it's true for all natural numbers n, but this right here would disqualify 1 because 1 is not greater than 1 1/4. So actually then this would have proved that this is not true for all value natural numbers n. But this is where I thankfully spotted my mistake, because this is not meant to be a minus 6, it's meant to be a plus 6 like on this side. So let's just quickly fix that up, and I'll just do all my fixes in blue. So we now have, okay, it's confusing to just have the one line in blue. Right, so this is no longer minus 15, it is minus 3. And then there was okay, this and this gave us this 6 minus 3 gives us plus 3. Okay, and then we have, this is fine, this is fine, this is changing to minus 3. Okay, and then we corrected the zealousness. Added 3 instead. Well, we're adding 3 instead. And then over here, we now have a 3. Right, okay, now that's looking better. Okay, so this is, Right, okay, so now what this is telling us is for any value of n, any number n greater than a quarter, this inequality will be true. This inequality will be true. And indeed, because we only care about the natural numbers n, right, then we only care about 1, 2, 3, 4, and those are all numbers bigger than a quarter. So all n are greater than a quarter, therefore Tn plus 1 is greater than Tn for all n in the natural number set. And that is what we needed to prove. Okay, so yeah, I need to be less sloppy. I've been making so many mistakes with this paper. Anyway, I do hope that even in my fumbling about, even in my temporary confusion, in my comeback, all these detours are helpful. That is the biggest cry of my heart. Thanks for tuning in as usual, and yeah, check you another time for another chat. And of course, if you had another way of thinking about the problem, do share. Yeah, let's wrap it there.